Hi everyone, welcome to the lecture number 15 of higher order differential equation unit number 3. In this lecture we are going to start solving next type of differential equations which are Cauchy's and Legendre's differential equation. Okay, these differential equations are linear differential equation with variable coefficients. Okay, so far we have studied the linear differential equations with constant coefficients. To solve this differential equation we reduce them to LD with constant coefficients. Okay, because we have studied only LD with constant coefficients. So whenever we have Cauchy's or Legendre differential equation in front of us, their coefficients will be variable. We need to reduce them to constant coefficient using substitution. Okay, there are some standard substitution available for both the differential equation that we use to convert them to LD with constant coefficient. Then we solve using previously discussed method. So whatever methods we have discussed so far, general method, variation of parameter, shortcut methods, by using the remaining part can be solved. Now we'll define the both differential equations. What type of differential equations are called as Cauchy's differential equation and Legendre's differential equation that we are going to discuss. Here is the definition. Cauchy's linear differential equation. First definition: an equation of the type a0 x raised to n dn y dx raised to n plus a1 x to the power n minus 1 dn minus 1 y by dx raised to n minus 1 dot an minus 1 x dy by dx plus an y equal to f of x. It's called Cauchy's Legendre's differential equation. Now if you see the previous if you see the definition of linear differential equation with constant coefficient, this definition is quite similar to that, only here the new terms are present, the powers of x. These are the variables, right? X is a variable. So here we have in the coefficient of derivatives powers of that variable, x variable. Okay, so if the derivative is of order n and the same power x has for all the terms involved in the differential equation, these type of differential equations are called as Cauchy's differential equation. Here the order of the derivative is n minus 1, therefore the power is of x is n minus 1. That we have to check whether the order of derivative and the power of x is same or not. Such a type of differential equations are what? Cauchy's differential equations. Now similar definition the Legendre differential equation has. Legendre's linear differential equation is defined as an equation of the type a0 ax plus b raised to n dny by dx raised to n plus a1 x plus b raised to n minus 1 dn minus y by dx raised to n dot plus an minus 1 x ax plus b dy by dx plus an y equal to f of x is called Legendre's differential equation. Okay, Legendre's linear differential equation. This is linear also. Okay, now what is the difference between two? Instead of x, the factor ax plus b we have in Legendre's case. This ax plus b is a linear factor in x where a and b are constant. When we put a equal to 1, b equal to 0, we get this equation. Okay, means Legendre's Cauchy's differential equation is a particular case and this is the general case. Okay, this type of differential equation. Okay, so whenever we have linear factor of this type, some constant ax plus some constant involved in the coefficient of derivatives and the same power of that factor, if the same power of that factor appears which is equal to order of derivative, then such type of differential equations are called as linear differential, Legendre's linear differential equation. Now we are going to discuss how to reduce this differential equation to LD with constant coefficient so that can be solved by using previously discussed method. Okay, so that is we are going to discuss substitutions. Okay, for both the differential equation. Here are the substitution. For Cauchy's differential equation, we put x equal to e raised to z. Okay, so this substitution is fixed for all Cauchy's differential equations. Okay, whenever you will find the differential equation of the type Cauchy's differential equation in the example, for that problem you put x equal to e raised to z, and that is the nothing but z equal to log x. Okay, means we are changing our variable x to z. In terms of z we are writing. Okay, so x dy by dx, under this substitution the values of these derivatives, these terms get changed. X dy by dx becomes capital dy where d is the d by dz. As we have changed our variable x to z, okay, therefore derivative with respect to x will get converted to derivative with respect to z. Means we are going to change our differential equations variable. Okay, means your original differential equation will be in terms of y and x, and the new differential equation after transformation will be in terms of y and z. Okay, therefore the solution you will get of y in terms of z first, and then by using the back substitution z equal to log x, you are going to get the solution in terms of x. So whenever we do substitution, at that time back substitution also we do in solution. Okay, so these are the quantities that you must memorize, because this type of terms will be there. X dy by dx we are going to replace by dy, so that this x will get removed and your coefficients of derivatives will become constant. Okay, these are the variable coefficient, they will get changed to these terms dy, capital dy. Okay, where capital D is d by dz. X square d2y by dx square will get replaced by d into d minus 1 y. X cube d3y by dx cube will get replaced by d into d minus 1 into d minus 2 y. Okay, and so on, dot dot dot. If you take x raised to 4 here, then d into d minus 1 into d minus 2 into d minus 3, up to 3 you have to go. If 3 is here, up to 2 you need to go. If 2 is here, up to 1 you need to go. Okay, like that you have to replace the terms in the differential equation. Okay, so after this replacement, you will get some differential equation in terms of y and z that can be solved by using the previously discussed method. Mostly we use shortcut methods to solve this differential equation. Okay, and once you get the solution, you will get the y value of y in terms of z, and there after getting solution you need to do back substitution to get the solution of y in terms of x. Okay, after examples you will understand it, how we are going to do it. Now next, in the case of Legendre's differential equation, we put that factor ax plus b equal to e raised to z, that is z equal to log of ax plus b. We are going to put a for ax plus b e raised to z. After this substitution, the values of ax plus b dy by dx will get replaced by a into dy. So in Cauchy's method we have dy only, here we get a additional, okay, which is the coefficient of x. Fine, where again the value of capital D is d by dz. The factor ax plus b square d2y by dx square will get replaced by a square into d to d minus 1 y. And the factor ax plus b cube d3y by dx cube equal to a cube d into d minus 1 into d minus 2 y. Okay, and so on. Okay, for the next power also you can do, but we have written only up to 3 power, because in examples we are going to have examples only up to order 3 differential equation we are going to have in examples. Okay, therefore only up to order 3 we have discussed. So what is the change into here? No a, and here a square, that terms will get added. Okay, so after this we are going to start with examples. So in examples, first you write the substitution, then you write these values, and then you replace these values in the given differential equations. Okay, so let us see how to do it by taking one example. Now I am going to give mixed problems. You need to identify whether it is Legendre's or Cauchy's. Then we are going to obtain its solution. Okay, now example. This is the first example. Solve x square d2y by dx square minus x dy by dx plus 4y equal to cos of log x plus x into sine of log x. Okay, now if you see the derivatives, here we have order 2 derivative, in its coefficient we have x square. Here first order derivative, in its coefficient power of x is 1, and here no derivative, so power of x is 0, that is constant term 4 into y. Okay, so this is a Cauchy's differential equation. Here we don't have factor, only powers of x we have. Okay, so clearly this is Cauchy's differential equation. So you can write in solution that given LDE is Cauchy's LDE. Okay, so as this is Cauchy's LDE, we are going to put x equal to e raised to z. So this will imply z equal to log x. This value will need when we do back substitution, z equal to log x. Okay, for this substitution, the value of x dy by dx we are going to replace by capital dy. The value of x square d2y by dx square we are going to replace by d into d minus 1 y. Okay, and there is no cubic term, so only these two values we are going to replace, where capital D is d by dz, right? Therefore, on using above values in given differential equation, we get x square d2y by dx square we are going to replace by d into d minus 1 y. X dy by dx we are going to replace by dy, and 4y as it is plus 4y. Right hand side, cos of log x, x is e raised to z, so log of e raised to z will be z, so it will be cos z x into sine of log x, log x is z, so it will be x is e raised to z, so it will be e raised to z sine z. So this will be the new differential equation. So let us rearrange the terms. If you multiply by, y can be taken common. So if you multiply, you will get d square minus d, this minus d, and plus 4. Minus d will be minus 2d plus 4y. So this will be the differential equation. Right hand side will be cos z plus e raised to z sin z. Now this is the new differential equation with constant coefficient we obtained. Okay, and this is in terms of z. Now from this step onwards, we are going to do calculation like previously discussed method. Okay, and after getting solution, you will get the value of y in terms of z, because the right hand side is a function of z, and this capital D is d by dz. Okay, so once we get that solution, in that solution we are going to replace z by log x to get our, this is log x. Okay, z by log x to get our required solution. So let us start. First consider auxiliary equation is d square minus 2d plus 4 equal to 0. It is the perfect square of d minus 2 bracket. Sorry, it is not perfect square. Its roots will be minus b. D equal to minus b means minus 2 plus minus b square is 4. 4 minus 4 is 16 divided by 2a. So 2 by 2 will be, real part will be 1. 4 minus 16. 4 minus 16 is minus 12. Minus 12 can be written as minus 4 into 3. The root of minus 4 is 2i. 2 by 2, 1. So it will be plus minus root 3 by 2 I. So 2 will get cancelled, sorry. Plus minus root 3 I. So this will be the roots. Therefore CF for this imaginary pair of root e raised to x, 1 is the alpha, C1 cos root 3x, sorry, x, not x, it is z. It is z because the differential equation in terms of z. So that care we have to take, C2 sine root 3 z. If you write this answer in terms of x, finally you can't do the back substitution. So carefully you write the answer in terms of z. So give this equation number 1. Okay, now the calculation for particular integral. The definition of particular integral is 1 upon phi of d f of x, but here we have f of z, so function of z. This is the value of phi of d, this is the function f of z. Now we'll operate this on both. Here we have two terms, so I will separate these two terms. Now here we have cos function, so let us apply the method of cosine. Okay, case number 2, we'll replace d square by coefficient of z is 1, so minus 1 square, that is minus a is 1, we replace it by actually minus a square, right? Here a is 1, so therefore we'll replace d square by minus 1. 1 square is 1. Here we have e raised to x into v case. So in e raised to x, that case, first I will do the substitution for this, minus 1 minus 2d plus 4 into cos z. First we take e raised to z outside, then we replace d by d plus a, where a is the coefficient of x in the power. So here the coefficient of z is 1. So we will replace d by d plus 1. So we will have d plus 1 square minus 2 into d plus 1 plus 4 outside sin z. Okay. Now we will get here 4 minus 1 3. So 1 by 3 minus 2d into cos z, and plus e raised to z 1 by, if you simplify this and do the addition subtraction of term, we will get finally d square plus 3. Okay, and operating on sin z finally. Now here we have linear factor, so in such a case we do the rationalization. After doing multiplying by divided by 3 plus 2d, we will get here 9 minus 4d square cos z plus e raised to z. Here also sine, method of sine, we will replace d square by minus 1 plus 3 sine z. Now replace again d square by minus 1. So here we will get plus 1. So it will become plus. So 9 plus 4 13. 3 plus 2d by 13 cos z. Plus this is 2 e raised to z by 2 sin z. Now this term is free of d. This term contains d. Operate this 3 plus 2d on cos. So we'll get 3 cos z plus 2 into derivative of cos is minus sin. So it will be minus 2 sin z divided by 13 plus e raised to z by 2 sin z. Now this is free of d. So this will be the final pi. Now add CF and pi. After adding CF and pi, we'll get e raised to z into c1 cos root 3z plus c2 sin root 3z plus e raised to z by 2 sin z plus 1 by 13 times 3 cos z minus 2 sin z. This is pi, this is CF. Now we have to do at the end back substitution. The value of e raised to z we are going to replace by x and z we are going to replace by log x. Okay. So after doing that, we'll get x into c1 cos root 3 log x plus c2 sin root 3 log x plus x by 2 sin log x plus 1 by 13 times 3 cos log x minus 2 sin log x in the bracket. Okay. So this will be the solution, final solution, general solution we call. Okay. After doing the back substitution. Now one problem of this type for practice. X square d2y by dx square minus 3x dy by dx plus 5y equal to x square sin log x. Answer for this problem is c1 cos log x plus c2 sin log x minus 1 by 2 x square log x into cos of log x. This is the CF and this is the pi. Okay, put x equal to e raised to z. Replace this x square d2y by dx square by d into d minus 1y, x dy by dx by dy, and where d will be dz, x equal to e raised to z. So x square will be e raised to 2z, sin of log x will be sin z. So try to solve the differential equation and get the solution. Like previously solved example you proceed, you will get this solution. So that's it from this lecture. More problems on Cauchy's and Legendre's differential equation we are going to cover in coming lecture. Okay, thank you.